Our next topic is that of strong acids and bases and their reactions. And so what do we mean by a strong acid or base? Here's some examples where we have a hydrogen with one of the halogens, chlorine, bromine, or iodine, HNO3, HClO4, and H2SO4 are all examples of strong acids. And a strong acid is one that's basically a solution of H3O+. And the counterion, Cl- or Br- is just there to keep the solution electrically neutral. So if we have a 0.1 molar solution of HCl, that actually looks like H plus of 0.1 molar and the counterion Cl- of 0.1 molar to keep the solution neutral. H2SO4 is a little different because there's 2 protons for every molecule of H2SO4. And so we have a concentration of H plus that's 0.2 molar and SO4 of 0.1 molar. This is still electrically neutral because the charge on the SO4 is -2, whereas that on the proton is +1. So if you add that up, the charge exactly cancels. The most common strong bases are the alkali metals with an hydroxide, so sodium hydroxide and potassium hydroxide. And just as the strong acids are basically solutions of H3O+, these are essentially solutions of just OH- with the sodium or the potassium ion there to keep the solution electrically neutral. So a 0.1 molar solution of sodium hydroxide would correspond to 0.1 molar in OH- and 0.1 molar in sodium. So a strong acid is essentially a solution of H3O+, and a strong base is essentially a solution of OH-. So if we mix together an acid and a base, we're basically a strong acid and a strong base. We're reacting H plus with OH-, and we can get the reaction between these two from the reaction we introduced earlier, H2O going to H plus and OH- with 10 to the -14. If we reverse this reaction, now we're viewing it as H plus, strong acid, reacting with OH-, strong base, to form water. So this is a strong acid-base neutralization reaction. And the equilibrium constant is 1 over Kw, since we reversed the reaction. And that is 1 times 10 to the 14th. So this is a very large K. This reaction lies very, very far to the product side. And so in thinking about reactions of strong acids and strong bases, we're in what is almost a limiting reagent situation. K is so large the reaction lies predominantly to the product side of water, and so whichever is limiting H plus or OH- is what limits the reaction. So as an example of a strong acid-base reaction, we'll consider the important case of titration. And in this case, we're titrating a strong acid with a strong base. So let me bring up the virtual lab. And what I have here is a 25 milliliter solution of 1 molar HCl. So you can see it's basically a solution of H plus with a concentration of 1. And the counterion Cl- is there to keep the charge balanced. OH- is 10 to the -14, so that the product of the two is Kw. And in the burette, I have 1 molar NaOH. So this is essentially a solution of OH- of 1 molar and the counterion sodium to keep the solution neutral. I'm going to slowly add the base to the acid, but before I start, let me save a copy of this, and I'll label it as the solution from 0 milliliters of base being added. And I'll save copies as we move through the process of adding the base. So let me begin. I'm going to put a 1 down here into the transfer, so every time I hit the pour button, I'll be pouring 1 milliliter. Let me start off by adding a milliliter. You can see the pH changed. It started at 0 because the concentration of H plus was 1 molar, corresponding to a pH of 0. And now it's gone up to 0.03. And I continue adding base. The pH is rising slightly, but nothing too drastic. And at this point I've added 10 milliliters of base to the acid. The pH has gone up from 0 to 0.36. And let me save a copy of this. I'll rename it to 10 milliliters. Put it off here to the side. Let me go back to continuing to add solution. So I'm adding strong base to my strong acid. And now the pH is starting to change a bit. I started at 0, it's up to 1. And I've added 13 milliliters, or actually 23 milliliters. At this point I've added 24 milliliters. I started with 25 milliliters of acid. I've added 24 milliliters of base. You can see the number there. And the pH has gone from 0 to 1.7 about. Again, let me save a copy of this. And I'll name it 24 milliliters. And now let me add 1 more milliliter, and you can see a very strong change in the pH going up to about 7. So let me save a copy of that. That's at 25 milliliters. I'll add 1 more drop of base, 1 more milliliter, and the pH jumped up to 12. And you can see I've added 26 milliliters to this, so I'll label it 26. Oops. 26 milliliters. And let me continue adding base to the solution. You see the pH is continuing to rise, and I've now added 50 milliliters of base. Let me do my final copy. As 50 milliliters. And so if we go back and re-look at these, we started with a pH of 0. Adding 10 milliliters led to a slight increase. 24 got us up to 1.7. At 25 we went to 7. At 26 we went to 12. And then from then on we just rise from 12 to 13. So there was this very big change between 24, 25, and 26 milliliters. And so now we're going to do the calculations to see why it is that that's happening. This is showing a titration curve. So on this axis here, we have the pH. And here we have the amount of base added. And you can see we start off with a pH of 0. The pH rose gradually up to about 24. Then at 25 we went to 7. A little past that, we're all the way up at close to 13. And then it just rises gradually beyond that. So why is it that the pH stays so steady, then all of a sudden jumps at this point before leveling off again? And so we're going to calculate the pH of each of these solutions that I saved during the titration. So to start with, we want to know what is the pH of the starting solution. We had 25 milliliters of 1 molar HCl. Here's what was in the virtual lab. You can see that HCl exists as H plus and Cl minus, so we have a 1 molar solution of H plus. Put that into the formula for pH, and we get a pH of 0. So next we'll consider the pH of the solution after we've added 10 milliliters of base. And back here, so I've added 10 milliliters. Here's the results from the virtual lab. Let's see if we can get those on our own. So the first thing we have to take into account is the dilution. We've added 10 milliliters of base to 25 milliliters of acid. So the final volume is 35 milliliters. We started with 1 molar HCl. Its initial volume was 25. Its final volume is 35, which gives us 0.71 molar HCl. Sodium hydroxide, we added 10 milliliters. The final volume is 35, so we have 0.29 molar solution. We've added a strong base to a strong acid, so our reaction is H plus OH minus going to form water. And our initial amounts are 0.71 and 0.29 molar. And this reaction has a very large K, 10 to the 14th, so we're best off starting by pushing the reaction to completion. OH minus is the limiting reagent, so we'll subtract 0.29 from both H plus and OH minus. And this gives us a better start for an equilibrium calculation, where we've pushed the reaction all the way to the product side. OH minus ran out, it's the limiting reagent. So the first approach we're going to use is similar to what we did in the previous section of the course, where we do a full equilibrium treatment of the system. And then I'll show you a much faster approach that you definitely want to use because it gets you everything you need to know in a much quicker manner. But let's start to make a connection to the way we did things previously. We'll introduce a change from this better start position of gaining X of H plus and OH minus, losing X of water. Losing the water doesn't matter because we assume there's plenty of water present, an infinite amount of water. And this gives us an equilibrium expression, or introduces the unknown X that gives us the concentrations of H plus and OH minus at equilibrium in terms of a single unknown. And we can now move on to solve for X using our equilibrium expression of 10 to the minus 14 is the product of H plus and OH minus. Putting our equilibrium expressions for H plus and OH minus. And we could go about solving for X. But it's best at this point to realize that X might be small compared to 0.42. After all, this reaction lies very far to the product side. We expect it to only come back a little bit. And so we'll assume that X is much less than 0.42 and check our approximation when we're done. This allows us to simplify the 0.42 plus X to just 0.42. And now we can solve that for X, get 2.4 times 10 to the minus 14. And we should always check our assumption. 10 to the minus 14 is certainly much smaller than 0.42. So this is a very good assumption that we made to simplify the problem. And now we look back, we solved for X. We can look back at H plus and OH minus in terms of X. Find that H plus is 0.42. The addition of X to such a small number as 10 to the minus 14 to 0.42 doesn't matter. And OH minus is equal to X of 2.4 times 10 to the minus 14. And we'll translate that into pH and pOH by taking minus the log of those numbers. And get 0.38 for the pH, 13.6 for the pOH. We can compare that up here with what the virtual lab found. It has 0.36 for the pH, concentration of OH minus of about 3 times 10 to the minus 14. And this is, the reason that there's some disagreement is that the assumption that Kw is 10 to the minus 14 is only good to about 2 significant figures or so. And so We can compare our results to those in the virtual lab. The pH is 0.38 that we got. The virtual lab is saying 0.36. If we look at the concentration of OH minus, we see a slight disagreement. That we have 10 to the minus 14. The virtual lab said 3 times 10 to the minus 14. If we go back, this is actually an effective temperature. Kw is equal to 10 to the minus 14 at room temperature, but it's actually a fairly strong function of temperature. And now that the solution is cooled down to room temperature, we're getting 2.4 times 10 to the minus 14, which is in agreement with our calculation. If we heat this up by a small amount, say to 30 degrees, we'll see that the concentration of OH minus actually changes to 3.3 times 10 to the minus 14. And this is reflecting the fact that Kw has a dependence on temperature. And we'll come back to that later and talk about that more. As it cools down, the concentration of OH minus is going to go back to what we calculated it should be at room temperature. When I started the process in green, I said that this was a slow approach to the calculation and that there is a much faster approach. And that's what we're going to do now. So let's go back to our initial dilution calculation where we said we have 0.71 molar H plus reacting with 0.29 molar OH minus. We do a limiting reagent step where we say if this reaction goes all the way to completion, then I'll have 0.42 of H plus left over. So let me come down here, and from that point where I've done a limiting reagent calculation, let me show you a much faster way to do the rest of the calculation. I can just say my concentration of H plus is 0.42, which corresponds to a pH of 0.38. And then the sum of pH and pOH has to be 14, so I can get the pOH by taking 14 minus pH to give 13.6. So this lower calculation is clearly a much faster approach to get the same answer, pH of 0.38 and pOH of 13.6. Why is it that it's valid? And the reason is that 1 over Kw is 10 to the 14th, so this reaction does lie very, very far to the product side. So this assumption we made that x is small is always going to be valid. This reaction is only going to come back a very small amount. So at this step here where we said we can take 0.42 plus x and replace it by 0.42, that leads us directly to a concentration of H plus that's 0.42. Which is what we did down here. We said, let's take this 0.42, say the concentration of H plus is 0.42, and that gives us the pH. The second part is getting pOH by taking 14 minus pH. From this stage in the calculation on, all we're doing is saying if the concentration of H plus is 0.42, what's the concentration of OH minus? And so we're using Kw equal to H plus times OH minus to solve for OH minus, giving H plus. The idea that pH plus pOH is equal to 14 is equivalent to this equilibrium expression. It's just the log of that equilibrium expression. So taking 14 minus pH to get pOH is exactly equivalent to solving the Kw expression from this point down. So the take-home message is that when you're doing strong acid, strong base calculations, you can just do a limiting reagent calculation, figure out what is left over after this reaction goes to completion, and then figure out the pH and the pOH from that result. So we've calculated the pH at the beginning. Started with 1 molar solution of HCl, so the pH was 0. We just added 10 milliliters of base to the acid and got a pH of 0.36. Next we're going to go to 24 milliliters. This is the point at which the pH is starting to rise. It changes from 0.36 at 10 milliliters to 1.7 at 24 milliliters. So let's do the calculation and see why that's happening. So we're adding 24 milliliters. Here's the result from the virtual lab. So the process proceeds similar to what we just did. We start with the dilution calculation. we've added 24 milliliters of base to 25 milliliters of acid, so the total volume is 49. HCl gets diluted by a factor of 25 over 49, its initial volume over the final volume. And NaOH gets diluted by a factor of 24 over 49. So the concentrations are becoming fairly equal. HCl is 0.51, NaOH is 0.49. So we move on to our reaction, which is H plus OH minus to give water. Our initial concentrations are 0.51 and 0.49. We do the limiting reagent calculation of OH minus is limiting, so we subtract 0.49 from both concentrations and get 0.02 molar as our starting concentration for H plus. That leads to a pH of 1.7. Take minus the log of 0.02, you get 1.7. And we can get the pOH by taking 14 minus the pH to give 12.3. And if we want to know the concentration of OH minus, we can do that by taking 10 to the minus pOH. 10 to the minus 12.3 is 5.8 times 10 to the minus 13. We can see good agreement with what is happening in the virtual lab. So why is the pH starting to change? It's because we're starting to add almost as much base as we had acid. So starting off with an initial concentration of 1 molar acid, we've added enough base to lower its concentration to 0.02. So the pH has gone from 0 up to 1.7 at this point. So we've now looked at 24 milliliters. As we went from 10 to 24, we had a rise from 0.3 to 1.7 in the pH. If we add 1 more milliliter, 25, we're getting a pH of 7. And why is that happening? If we look at calculation for addition of 25 milliliters of 1 molar NaOH, we again start with the dilution calculation. So we have equal amounts, 25 milliliters of acid, 25 milliliters of base. The total volume is 50 milliliters. In both cases, both the acid and base started with 25 milliliters. The final volume is 50. So they have equal concentrations of 0.5 molar. We write down our reaction between the strong acid H plus, the strong base OH minus. And we see that they have equal initial amounts, so they consume each other. And now the limiting reagent calculation gives just neutral water. So we have a neutralization occurring, and the pH and the pOH are therefore equal to 7. So the origin of the rapid change in pH is starting to become apparent. We started off with acid. As we add base to the acid, we're slowly consuming the H+. The OH- we're adding is consuming H+. When we get to 25 milliliters, we've added as much base as we had acid to start, so they completely neutralize each other, and we're back to neutral water. Now we're going to go 1 milliliter past that point, where we've added base, and the pH has risen from 7 up to 12.3. So we're going to look at the addition of 26 milliliters of base to our solution. And again, we start with the dilution calculation. So we had 25 milliliters of acid to start with. We've added 26 milliliters of base, so the total volume is now 51. For the acid, we have a dilution factor of 25 over 51, whereas for the base it's 26 over 51. So we have more base than we have acid at this point. We've passed the point where the base is equal to the acid, and we're into the basic region of the titration now. We can write our reaction between the strong acid and the strong base, and putting our initial conditions. And now we see a slightly different thing occur in the limiting reagent calculation, in that we're subtracting off, H plus is the limiting reagent, so we subtract off 0.49, and we get 0 for the H plus concentration and 0.02 for the OH minus. So in this case, what we should do is calculate the POH. So we know the concentration of OH minus is 0.02, which means we know the POH is minus the log of that of 1.7. And the part where the reaction returns a little bit from being all the way a product to being equilibrium, we can handle by saying the pH is 14 minus 1.7 or 12.3. If we want the concentration of H plus, we can say H plus is 10 to the minus pH, or 10 to the minus 12.3, or 5 times 10 to the minus 13. So in doing strong acid, strong base reactions, depending on which species is the limiting reagent, you change your procedure slightly. So back before we reached the neutralization, up here, the limiting reagent minus, there was some H left over. We would take that concentration of H plus, use it to calculate pH, and then use 14 minus pH to get POH. And this is because H plus is the dominant thing in solution. There's almost no OH minus present. If we look at the results up here, there's 10 to the minus 13 of OH minus, 10 to the minus 2 of H plus. H plus is the dominant thing. We calculate the pH, get the POH from the pH. Down here, the limiting reagent is H plus, so it's OH minus that's present in large amounts, 10 to the minus 2 versus 10 to the minus 13 for H plus. So we calculate the pH and then get the pH from the POH. And so now we'll consider the point at the very end of the titration where we've added 50 milliliters of base to 25 milliliters of acid. And now our final volume is 75 milliliters. If we look at the dilution factors for the acid, we have 25 over 75 to give 1/3 molar. For NaOH, we have 50 over 75 to give 2/3 molar. So we have twice as much base as we had acid to begin with. We write down our strong acid, strong base reaction and the initial concentrations. Limiting reagent now is H plus, so we subtract 0.33 from both H plus and OH minus to get 0.33 molar OH minus. We're way into the basic part of the titration. So we calculate POH by taking the OH concentration of 0.33. POH is minus the log of that, or 0.48. We get pH by taking 14 minus POH to get 13.5. And then if we want the concentration of H plus also, we take 10 to the minus pH to give 3.2 times 10 to the minus 14. So now that we've had a detailed look at what happens at a number of points in the titration curve, let's step back and think about what's happening here. So here's the titration curve. pH is shown on this axis and volume of NaOH here. And as we add base to the acid, we saw the pH went up gradually and then jumped at this point, passing through neutrality of 7 to go over to a basic pH, and then stays relatively stable. We give a name to this point at which the pH jumps of the equivalence point. It's defined as the point at which the number of moles of base that you've added is equal to the moles of acid. And for strong acids and strong bases, at the equivalence point, the pH will equal 7. we'll see later when we start doing weak acids and weak bases that we retain the definition that at the equivalence point, the number of moles of base is equal to the moles of acid. The thing that changes from strong acids and strong bases is that the pH is no longer 7 at the equivalence point. So if we look over here at this side when the pH was acidic and we were just starting to add base, in that region the limiting reagent was the base, so all of the base was being consumed and we had leftover acid. That's why the pH remained acidic. At the equivalence point, we've added as much base as we had acid, and so they completely destroy one another, and we have a pH of 7. When we get to this point, beyond equivalence point, now the acid is the limiting reagent. So we've added more base than acid. The acid runs out, there's leftover base, and the pH becomes basic. In terms of calculations, over here, when the base was the limiting reagent and there was acid left over, we calculated the pH, and from the pH we got the pOH and therefore the concentration of OH minus. The situation is different somewhat over when the acid becomes the limiting reagent, since then you calculate the pOH and you get the pH from the pOH by taking 14 minus pOH. So we'll close with a series of questions about acid-base reactions and titration curves. The first one is this. Say we start with 100 milliliters of 1 molar HCl and we add solid sodium hydroxide. How many moles of sodium hydroxide would we need to add to get the pH to be 7? You should hit pause on your player right now and think about the answer, and then once you have an answer, hit play again. See you in a sec. Okay, you should have an answer to this question in your mind right now. So to get a pH of 7, this corresponds to neutralization. In other words, we've added as many moles of base as we had moles of acid to start with, or we're at the equivalence point in the strong acid, strong base titration curve. So the moles of acid is equal to the concentration of 1 molar times 0.1 liters, and that's how many moles of base we're going to want. So 0.1 times 1 is 0.1. So we need that many moles of base, and so if you said B, then you were correct. Neutralization question. In this case, it's a solution of sodium hydroxide that we're adding to the 100 milliliters of 1 molar HCl. And the question is, how many milliliters of 5 molar NaOH would you need to add to get a pH of 7? Again, please hit pause, think about an answer, and then once you have an answer, hit play again. Okay, so this is similar to the above in that we have 0.1 moles of acid and we need to neutralize it with 0.1 moles of base. We want to reach the equivalence point. So the moles of base is equal to its concentration, 5 molar, times the volume of base. And if we solve that, we get that the volume of base 0.1 moles over 5 moles per liter, or 0.02 liters, or 20 milliliters. So if you said B, you are correct. An even faster way to do this is to say that we have a 5 molar solution of sodium hydroxide and a 1 molar solution of HCl. So the base is 5 times more concentrated than the acid. So to get to a point where the number of moles of acid equals the number of moles of bases, we would need to add 1/5 the amount of acid we have present, or 100 over 5 to give 20 milliliters. So either approach is a good way to solve this problem. Okay, so we'll move on to the next question, which is, if I have 10 milliliters of 1 molar NaOH and I mix 7 milliliters of 2 molar HCl with it, Do I expect the resulting solution to be acidic, basic, or neutral? Please hit pause and think about what your answer will be. So in this case, we really just want to know whether we're at the acid or the base side of the titration. Are we over here, where we have more acid than we have base? Or are we over here, where we have more base than we have acid? So if we calculate the moles of base, we take the concentration of the base times its volume. We get 0.01 moles. We do the same for the acid. 2 molar times 0.007 liters gives 0.014 moles. And so we have more acid than we have base, which places us on the acidic side of the titration curve, so the pH is less than 7. So if you said A, that is the correct answer. Okay, and so our last question takes a little while to read. And it says that a comic book villain is holding you at gunpoint and making you drink acid, as comic book villains are wont to do. And she gives you 100 milliliters of a strong acid with a pH equal to 2. And you also have a beaker of strong base with pH equals 13. You're allowed to add the base to the acid before you drink it, and you'd be best off making the solution neutral before you do that, before you drink it. So how much base would you need to add to this acid to have a neutral solution? Again, please hit pause and come up with an answer on your own before hitting play again to hear our solution. So the issue here is really how strong is the acid compared to the base. We have an acid with a pH of 2 and a base with a pH of 13. So how do we think about the relative concentration of this acid versus the base? For the acid, we have a pH of 2, so the concentration of H plus is 10 to the minus pH, or 10 to the minus 2. For the base, the pH is 13. Base is really a solution of OH minus, so we want to think in terms of POH, which is 14 minus 13, or 1. And so this base is actually more concentrated than the acid by a factor of 10. So the base is 10 times more concentrated than the acid, so that means we would need to add 1/10 the volume of the acid. So the volume of the base should be 1/10 that of the acid, or 10 milliliters. So if you said 10, you foiled the comic book villain again, and you're allowed to go on to another issue. So I hope you enjoyed